Open your microwave and you know what you're getting. Scalding edges, a cold middle, and whatever you heat it up, coming out soft and soggy, never crispy. That's been true for almost every microwave sold since the 1950s. And for 80 years, nobody has fixed it. Not because nobody's tried, it's because the core technology inside your microwave hasn't fundamentally changed since it was built for war. But in labs and factories across China, engineers are finally attacking that 80-year-old problem head-on. And the same idea behind their fix is now showing up somewhere far bigger than your kitchen. The story of your microwave starts with a candy bar. In 1945, a self-taught engineer named Percy Spencer was walking through a Raytheon radar lab in Massachusetts when he noticed a chocolate bar in his pocket had melted. He'd been standing next to a magnetron, the vacuum tube Raytheon mass-produced to power Allied radar during World War II. Spencer got curious, held a bag of unpopped popcorn kernels up to the tube, and watched them pop. Then he tried an egg, which exploded and left him cleaning yolk off the lab wall. 2 years later, Raytheon released the first commercial microwave oven, a 6-foot-tall machine called the Raider Range that weighed roughly 750 pounds and cost the equivalent of about $58,000 today. It took another 25 years before the technology shrank down small enough and cheap enough to land on a kitchen counter. Here's what never changed in all that time. A magnetron cooks food by exciting the water molecules inside it until they vibrate fast enough to generate heat from the inside out. That's genuinely useful for melting butter or reheating soup, but it also means a microwave can't produce the one thing that makes food taste finished: a dry, high heat surface that browns and crisps. Without that surface heat, you never get the Maillard reaction, the same chemical process that turns bread crust golden or the edge of a steak dark. Run a frozen pizza through a microwave and the cheese melts fine, but the crust stays pale and limp because the machine physically cannot produce the kind of heat that would fix it. No patching gets around it. The physics sets a hard limit no sensor can undo. For decades, manufacturers patched around that limit instead of solving it. The turntable came first, spinning food so the hot and cold spots inside the cavity would even out over time. Those spots exist because microwaves bounce around a metal box as standing waves, stacking on top of each other in some places and canceling out in others. So one part of your plate sits in a wave peak and another sits in a dead zone. A turntable just moves your food through both. Then came humidity and weight sensors that guessed when food was done, then bolt-on grill elements that added a little top-down heat. None of it touched the actual problem. Manufacturers spun around it, sensed around it, and heated a little more around it, but the browning limit never moved. So who's actually trying to fix it? Here's something most people don't know while they're microwaving leftovers. There's a real chance the machine on your counter, whatever badge is on the front, was built in China. Galanz, headquartered in Guangdong province, became the world's largest microwave oven manufacturer by the late 1990s, holding roughly 40% of the global market. And in 2021, it went a step further, becoming the controlling shareholder of Whirlpool's China operations and buying its way into the very company that once defined the American appliance industry. Midea, also based in Guangdong, has since grown into the industry's other giant, ranked as the world's leading microwave maker. Galanz doesn't only sell microwaves under its own name either. It also manufactures for other retailers as a private label supplier, so a machine sitting on an American counter can be a Galanz build wearing someone else's logo. Now Chinese manufacturers are trying something different. Instead of patching around the microwave's core limitation, they're stacking multiple real heat sources into one machine and letting sensors decide how to use them. Galanz's Speedwave and Toastwave lines combine true convection, which circulates hot air the way a full-size oven does, with infrared heating elements strong enough to brown and crisp, plus a built-in humidity sensor that tracks moisture and adjusts automatically. It's a genuine 3-in-1 machine, closer to a countertop convection oven than a microwave with an air fryer bolted on the side. Midea has pushed the sensing side even further. Its AI Research Institute in Shenzhen has spent years training computer vision models specifically on Chinese cuisine, because Chinese dishes vary in shape, color, and texture far more than the standardized meals most food recognition software was originally built around, which forced Midea's engineers to solve a harder version of the same problem everyone else in this space is working on. Medea's fun oven used an internal camera to watch food as it cooked, matching what it saw against that training data to pick a cooking curve automatically, rather than making you guess at a dial. Even Whirlpool, the century-old American appliance giant, patented its own camera in microwave design in 2022, protecting the lens from heat and radiation with a specially coated shield. The engineers listed on that Whirlpool patent are based in Shenzhen, so even when the logo on the box says an American company, the camera vision engineering behind it is still running through the same corner of China as everyone else chasing this problem. If you're finding this rundown useful, go ahead and hit subscribe, because this channel tracks exactly this kind of shift happening quietly across the entire kitchen, one appliance at a time. None of what I described is cheap or universal yet. A combi oven with true convection and sensor cooking costs more than a basic microwave, and camera-guided food recognition is still mostly confined to flagship models and research labs rather than the appliance in a typical kitchen. It's early, and there's a real chance some of these specific products get replaced by better versions before they ever go mainstream. What's harder to ignore than any single product, though, is that this same instinct, stack precision, instead of relying on one blunt method, is showing up somewhere with far higher stakes than your dinner. Since 1968, engineers have known you could theoretically collect solar power in space, where the sun never sets and clouds never get in the way, then beam that energy down to Earth using microwaves. A physicist named Peter Glaser proposed it first, patented the idea in 1973, and the US Department of Energy studied it seriously for years before shelving the project in 1979 as too expensive to justify. China picked the concept back up under a program called Jury, led by Duan Baoyan, a professor at Zhejiang University, and an academician at the Chinese Academy of Engineering. Duan's own team has spent years running ground tests on a facility built specifically to simulate the physics of a satellite kilometers overhead, and the problem they're solving sounds strange coming from a kitchen appliance video, but it's the exact same problem as your microwave, just at a completely different scale. A satellite can't blast microwave energy vaguely toward the ground the way your oven blasts it vaguely at a plate. It has to collect solar power, convert it, and fire it down through the atmosphere in an extremely narrow, precisely steerable beam that lands on a receiving antenna hundreds of miles below without drifting off target. Miss that target by even a small margin, and the energy never reaches the receiver at all, which is exactly why beam precision matters more here than raw power output. Earlier this year, Duan's team transmitted 1,180 watts across roughly 100 meters at their ground facility in Xi'an while holding that beam steady, and separately powered a drone in flight, delivering 143 watts to it from about 30 meters away. Those numbers are still a tiny fraction of what a real orbital station would need to deliver at commercial scale. Duan himself says the next real step is in orbit testing, and that it will be years before any of this comes close to paying an electric bill. So the next time your microwave leaves one side of your plate cold, that's not bad luck. That's a machine running on physics from 1945 that nobody upgraded because a bolted on grill element was cheaper than solving the actual problem underneath it. The people actually solving that underlying problem are working in facilities you've probably never heard of. In Foshan, in Shenzhen, in Xi'an, on tasks that range from a lukewarm bowl of soup to a beam of power crossing the vacuum of space toward a target hundreds of miles below. Different machines, different stakes, but the same idea driving both of them forward.